हेलो एवरीवन, हाय एवरीवन। आज हम इस वीडियो लेक्चर में सीखेंगे व्हाट इज न्यूक्लियोफिलिक सब्स्टिट्यूशन यूनिमोलिकुलर रिएक्शन। So having learned bimolecular substitution reactions, the second pathway which involves substitution at alkyl halides or substitution of alkyl halides is substitution nucleophilic unimolecular. So the heading for today's discussion will be substitution nucleophilic unimolecular, which is popularly written as SN1. So we have substitution nucleophilic unimolecular reaction. So this reaction is SN1. So S for substitution, N for nucleophilic, 1 for unimolecular. So coming to the molecularity of the reaction, molecularity of the reaction is 1. So this 1 represents the molecularity of the reaction. That means only one molecule is involved in the rate determining step of this substitution reaction. Second, this SN1 pathway or mechanism, a reaction occurs through two steps. This is two-step reaction. So reaction occurs in two step, whereas SN2 occurs in single step. SN1 occurs in two step. SN1 reaction proceeds via formation of a carbocation intermediate, whereas SN2 was through a transition state. Occurs via formation of carbocation intermediate. So look at this. In SN1, intermediate formation is there, that too carbocation. Whereas in SN2, transition state formation was there. So this is the difference between SN1 and SN2. SN1, this kinetics of this SN1, when we look at the kinetics of SN1, kinetics says rate of reaction is equals to some constant K known as rate constant into the concentration of alkyl halide. With respect to alkyl halide, order is 1, and with respect to nucleophile, the order is 0. So SN1 is 0 order with respect to nucleophile, meaning thereby SN1 does not depend on the nature and the strength of nucleophile, whereas SN2 was directly proportional to the nature of nucleophile. So whenever we have successful SN1 reaction, SN1 reactions are carried out either in absence of nucleophile or in presence of a very weak and dilute nucleophile. So nucleophile should be weak or dilute. If at all अगर आपको use करना है, then it has to be weak or dilute or absence of nucleophile. The reaction should be carried out in absence of nucleophile. Then अगर आप क्वेश्चन पूछता कि भाई if there is no nucleophile, how can this undergo nucleophilic substitution reaction? The solvent used in the reaction should always be acting as a nucleophile, and that type of reaction is known as solvolysis reaction. So in most of this SN1 reaction, the solvent itself plays the role of nucleophile. solvent plays the role of nucleophile. For this SN1 reaction, the solvent to be used is polar protic solvent like water, like ethanol, etc. So the reason is why we need to have a polar protic solvent. So look at this very carefully. In this case, look at it, there is a formation of carbocation, carbon with positive charge. So we have a positively charged species that is formed in this determining step. So these carbocations should be stabilized by solvent. Now these being positively charged, we need to have a polar protic solvent. So these polar protic solvent will stabilize this carbocation. So to increase the stabilization of carbocation, we need to have a polar protic solvent. So polar protic solvent or the polarity of solvent plays a very important role in SN1 mechanism. So while SN2 reaction is either weakly polar or non-polar solvent, and they do they protect. Whereas in case of SN1, we need to have a polar solvent and their polar solvent should have protic hydrogen. So this is the difference. So these solvent will stabilize the cation formed. Now we have this SN1. There is a formation of carbocation. The reaction involves in two steps. Kinetics is this. So order of reaction. Order of reaction is 1 plus 0. So this is first order, but occurs in two steps. Molecularity is 1. So this one and this one is different. The one in SN1 is due to its molecularity being 1, not due to order being 1. And this is a coincidence because the order and molecularity happens to be 1 each. Now coming to this reactivity order of alkyl halides. Now if we have different halogens, then the order is this. So again we have the same reason. Transition, look at this. There is a formation of carbocation. So carbocation formation means this RH bond should be a weaker bond. So in case of different halogens, as the size of halogen increases, bond length increases, bond strength decreases. So breaking of Ri bond is having required the least energy, whereas Rh bond breaking requires a higher energy. So Ri being the weaker bond can easily cleave, resulting in the formation of carbocation. So alkyl iodide is the most reactive for this SN1 reaction. Now if we have different types of alkyl group, then the reactivity order says tertiary alkyl is the most reactive, followed by secondary alkyl halide, followed by primary alkyl halide, and methyl halide is the least reactive. So if you look at this, the reactivity order is just opposite of that of SN2. In SN2, primary or methyl was the most reactive, whereas in SN1, tertiary is the most reactive. So if you look at this, why this is so? This reactivity order runs parallel to carbocation. We have seen there is a formation of intermediate, that is carbocation, and stability of carbocation says stability. Tertiary cation is most stable, followed by secondary, followed by primary. So since tertiary is the most stable, these tertiary cation can be formed from tertiary alkyl halide. So the most reactive combination will be tertiary alkyl iodide should be the most reactive for this SN1. So any factor which increases the stabilization of carbocation will increase the rate of reactions. So all this depends on the stabilization of cation. So this is the reason why polar protic solvent rate of reaction becomes faster. If polarity is decreased, rate again decrease. So considering this, tertiary benzyl group, tertiary benzyl halide is more reactive, is approximately having same reactivity to that of tertiary allyl halides, which is more reactive than secondary benzyl halide, whose reactivity is approximately same as that of secondary allyl halides, which is having similar reactivity to that of tertiary alkyl halide. So the reactivity of this is greater than primary benzyl, whose reactivity is similar to that of primary allyl, which is having similar reactivity to that of secondary alkyl, which is greater than primary. So any factor which increases the stability of cation will lead to the increase in rate of reaction. So this all explains based on the stabilization of carbocation for this reaction. Now this SN1 unimolecular substitution reaction, the product is found to be racemic mixture if the starting compound is a chiral compound. This forms a racemic mixture if that starting alkyl halide, if the starting alkyl halide is chiral. We'll explain while describing the mechanism of this reaction. So racemic means equal mixture of dextro D and levo form. 50-50 ratio of dextro form and levo form will be formed. That is what we call as racemic mixture. So racemic mixtures are optically inactive. So if we start with an optically active alkyl halide, for this substitution nucleophilic unimolecular, then the product will be optically inactive. This is optically inactive. If the starting compound is optically inactive, then there is no question of formation of racemic mixture. So racemic mixture is possible only when the starting alkyl halide is a chiral molecule which shows optical activity. Now this optical activity can be measured by an instrument which is known as spectrometer. Polarimeter that we have discussed is optical isomerism in stereoisomers in earlier classes, so I'm not going into details of this optical isomerism. So simply mean if the starting compound is optically active and if the reaction is proceeding by a SN1 pathway, then the product will be optically inactive. That means there is always a process which is known as racemization of the reaction, or a racemic mixture will be formed. Racemic mixture contains equal amounts of the dextro and the levo form of the same compound. So the optical rotation will be 0, means the rotation produced by dextro form will exactly be cancelled by the levo form. So this is the stereochemical difference between SN2 and SN1. SN2 says if the starting compound is chiral, there is complete inversion, Walden inversion. Inverted product will be formed. Whereas SN1 pathway says if the starting compound is chiral, the final product will be a racemic mixture. So we have discussed the reactivity order of reaction, nature of solvent, what is the nature of nucleophile, kinetics, transition state, molecularity state. This SN1 reaction shows common ion effect of X minus. That means in this reaction RH bond has to break, forming R plus and X minus. If we add X minus from outside, then the added X minus ion will show the common ion effect. That means that particular step should be the RDS, rate determining step. That means the rate determining step is the formation of carbocation. So in the rate determining step there is a breaking of CX bond. So if we add X minus from outside, that X minus ion shows common ion effect. As a result, the rate of reaction means equilibrium will be shifted to the backward. As the equilibrium is shifted to backward reaction, the rate of reaction will decrease. So this again proves that the rate determining step involves breaking of carbon halogen bond. This indicates breaking of RH bond in the rate determining step of the reaction. So these are some of the parameters that we use or that can be explained for this substitution unimolecular reaction. In SN2, increase in steric hindrance or crowding or increase in branching at carbon bearing halogen decreases SN2 reaction, whereas in case of this SN1, the branching at carbon bearing halogen or steric crowding increases the rate of SN1 because that branching will increase the stability of carbocation, whereas in SN2 that branching increases the steric hindrance in the transition state, so reactivity decreases in case of SN2, whereas in case of SN1 the reactivity again increases. Now this SN1 always competes with E1. SN1 always competes with E1 because in both cases there is a formation of carbocation. Both two-step reaction, both unimolecular, both requires polar protic solvent. The only difference is E1 requires base, SN1 requires nucleophile. So whenever we have base, SN1 and E1, to SN1 favors at low temperature, whereas E1 favors at high temperature. So by controlling temperature we can change the quantity of substitution product or elimination. SN1 requires weak nucleophile, whereas E1 requires weak base. So SN1 requires a weak nucleophile, whereas E1 requires a weak base. So by changing this nucleophile or basicity, we can change the quantity of SN1 or E1. So this thing has to be kept in mind. For both this reaction, reactivity of tertiary is more reactive than secondary, which is more reactive than primary. E1 again, reactivity is tertiary greater than secondary, greater than primary. SN1 requires polar protic solvent, same here, polar aromatic solvent, SN1 unimolecular. This is again unimolecular. This is through carbocation intermediate. This is also through carbocation intermediate. This is occurring in two-step reaction. This also occurs in two-step reaction. All the parameters are required except this. Look at this. So by checking temperature or nucleophilicity or the basicity of the reaction, we can change the quantity of substitution or elimination. So these will always be in combination with. So this is what I have mentioned you earlier. Alkyl halide is the most controversial, which always shows parallel reaction between substitution and the elimination reaction. So you have to keep in mind whether we are using a nucleophile or a weak base, or we are changing the temperature, low temperature or high temperature. Correspondingly, we will have substitution or elimination product. Now coming to the mechanism of these substitution. Mechanism, this involves in two steps. So the first step, suppose we have this. This is alkyl halide. So we have this R1, R2 and R3. In the first step, this breaking of CX bond takes place. So we break this CX bond. Both this electron is taken up by halogen. So this step is a reversible step in which we have carbon bearing 3 groups. This is R1, R2, R3, and a new carbon, this positively charged carbon, a p orbital is developed here. So if you look at this carefully, this first step is a rate determining step or the slow step of this reaction. In this slow step, there is a formation of X minus. So if we add X minus from X outside, so this X minus will undergo common ion effect, and because of this common ion effect, the equilibrium is shifted towards the left, and the rate of reaction will decrease. So this proves the breaking of RDS. So breaking of X minus is RDS in this reaction. Now we have look at this. Starting alkyl halide. If suppose this is chiral, we are assuming that this is a chiral, so this can form D or this may be L form. So this carbon is having sp3 and this is tetrahedral. Now after this breaking of CH bond, this carbon is sp2 and this is planar. Now in the second step of this reaction, so we have this planar cation So this is second step. So we have positively charged carbon R1, R2 and R3. Now these planar reacts with nucleophile. It reacts with nucleophile. So look at this. These nucleophile may combine with this p orbital when we give this product. So we have R1, R2, R3. So if you look at this product reaction and this product, that is retention of configuration. Having same configuration. So nucleophile attached to that side of starting alkyl line in which halogen was or the living group was present. On the other side, look at this. This is there's a 50% chance for formation of this retention product. On the other side, these being a planar, so these p orbitals are perpendicular to the plane of molecule. So on other side there is a 50% chances for this nucleophile to approach this p orbital. When this gives you this R1, R2 and R3. So if you look at this is inverted product. So there is a 50% chances for retention of the configuration or 50% chances for inversion of configuration. Why this is? Because these cationic carbon being planar, the nucleophile can approach from either side of the molecule. So this is a planar molecule, we have this p. So nucleophile has a 50% chances from this approaching this p orbital or 50% from this side. So there are 50-50 chances for retention as well as inversion. This retention inversion is responsible for the racemization of the product. This is what we call as racemization or formation of racemic mixture if the starting compound is chiral. So this racemization depends on the stability of cation. If the cation is much more stabilized, it can exist longer in the solution. As it can exist longer in the solution, chances for 50-40 the reaction will be more. So increasing the stability of this cation increases the chances for racemization. Increasing stability depends on two factors, that is polarity of the solvent. If the polarity of the solvent is increased, then the stability of cation increase, then racemization increases. Now branching at this carbon, if this is increased, then also stabilization of carbon in cation increases. So this is the reason we have explained these occurs in tertiary alkyl iodide. So look at this, breaking bond CX. So Ci being the weakest bond can easily flip. So the equilibrium will be shifted in the forward direction. Starting with tertiary alkyl line will give you tertiary cation. So tertiary cation is more stabilized. So this is the reason why aromatization or benzylic or allylic system is more stabilized or more reactive, because allylic cation or benzylic cation is resonance stabilized. Because of this resonance stabilization, this stability increases. So this is the mechanism part. Now this being occurring in two different steps, the energy profile of this SN1 includes this. If we draw the energy profile of SN1, that is reaction coordinate and the potential energy, this is Rx, this is Rmu product, this is intermediate R, this is transition state 1, transition state 2, this is the intermediate carbocation. So this is the energy profile. So as this, look at this transition state formation 1, that is breaking of this Rx, that is CX bond. So at this particular point CX bond breaks. The moment CX bond breaks, this is being stabilized due to hyperconjugation, resonance or stabilization by solvent. So this stability increases, potential energy decreases. Now this being stabilized by solvent, before this reacts to give you the product, the layer of solvent should be removed so that we have this free cation. So this removal of layer of solvent again requires energy, so this slightly increases and resulting in the formation of transition state 2. So this also indicates the two-step reaction. So the activation energy for this transition state 1 is more, so this is the rate determining step, or this is the slow step, this is the fast step. So this is SN2 mechanism and energy profile of SN1 pathway. Now let me give you some examples here. This is benzene, CH3, CH3I, this reacts with H2O. So if you look at this is the tertiary and this is also benzenic system. So this is a much more stable. So these react with water. So look at this. Water is a solvent here. Oxygen of water contains 2 numbers of electrons. So this solvent itself is acting as a nucleophile, and this replaces I minus, and this gives you OH compound. Take this PH CH3 CH2 CH3 Br. This reacts with CH3OH methanol. So methanol is a solvent, and this solvent also contains oxygen, which is having lone pair of electrons. So this is acting as a nucleophile. So we have PH CH3 C2H5 OCH3. Take this CH3 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 CH2I CH3. This reacts with water. Now look at this. This is secondary. So the first breaking of this bond gives you secondary cation, and as I have mentioned you earlier, whenever there is a carbocation formation, carbocation will always try to rearrange itself to a more stable. So the first cation reform will be secondary. Secondary will rearrange to a more stable tertiary by hydride shift, and this gives you the product CH3 COH CH3 CH3 CH3. Same here, CH3 CH3. If we have this hydrogen, then same again by reaction with this CH3OH. First this will give you secondary cation. Secondary will undergo hydride shift. By this hydride shift, tertiary cation will be formed, and this will be the final product. So CH3 COCH3 CH3. This is CH2 CH3. So whenever there is abnormality in the product formation, this is because of carbocation formation. So this is SN2 2 and SN1 reaction. So these are the two possible pathways by which substitution reaction takes place in alkyl halides. So this is a brief summary or a brief idea or a brief outline for substitution nucleophilic and alkyl halide system. So with this we'll conclude this substitution reaction.